Can you maybe explore the possible alternatives to the Big Bang theory?
So there are many alternatives, starting with the singularity, quantum cosmologically demanding singular origin of the universe. That stands in contrast to these other models, in which time does not have a beginning. And many of them feature cycles, at least one cycle, possibly infinite number of cycles, called by Sir Roger Penrose, and they all have things in common. These alternatives, as does the dominant paradigm of cosmogenesis, which is inflation. Inflation is can be thought of as this spark that ignites the hot Big Bang that I said we understood. So it's an earlier condition, but it's still not an initial condition. In physics, imagine I show you a grandfather clock or a pendulum swinging back and forth. You look away for a second, you come into the room, pendulum swinging back and forth. Alex, tell me, where did it start? How many cycles is it going to make before you can't answer that question without knowing the initial conditions. In a very simple system, like a one-dimensional simple harmonic oscillator, like a pendulum, think about understanding the whole universe without understanding the initial conditions. It's a tremendous lacuna, a gap that we have as scientists that we may not be able to, in the inflationary cosmology, determine the quantitative physical properties of the universe prior to what's called the inflationary epoch.
So you're saying for the pendulum in that epoch, we can't, because you can infer things about the pendulum before you show up to the room in our current epoch, correct?
Right. Yeah. So if you look at it right now, but if I said, well, when will it stop oscillating? So that depends on how much energy it got initially. And you can measure its dissipation, its air resistance. You had infrared camera. You can see it's getting hotter maybe. And you could do some calculations. But to know the two things in physics to solve a partial differential equation are the initial conditions and the boundary conditions. Boundary conditions, we're here on Earth. It has a gravitational field. It's not going to excurse or, make excursions, wildly beyond the length of the pendulum. It's not, it has simple properties. And this is in other words, you can't tell me, when did the solar system start orbiting in the way that it does now? In other words, when did the moon acquire the exact angular momentum that it has now? Now, that's a pretty pedestrian example, but what I'm telling you is that the inflationary epoch purports and is successful at providing a lot of explanations for how the universe evolved after inflation took place and ended, but it says nothing about how it itself took place. And that's really what you're asking me. I mean, you don't really look what you care about, like Big Bang nucleosynthesis and the elements got made and these fusion reactors and the whole universe was a fusion reactor. But don't you really care about what happened at the beginning of time, at the first moment of time? And the problem is we can't really answer that in the context of the Big Bang. We can answer that in the context of these alternatives. So you asked me about some of the alternatives. So one is aeon theory, the conformal cyclic cosmology of Sir Roger Penrose. Another one was really popular in the 60s and 70s until the discovery of the primary component of my research field, the cosmic microwave background radiation, or CMB, the 3 Kelvin all-pervasive signal that astronomers detected in 1965. That kind of spelled the death knell, in some sense, to what was called the quasi-steady state universe. Mm-hmm. And then there was another model that kind of came out of that. You hear the word quasi, so it's not steady state. Steady state means always existed. That was a cosmology Einstein believed until Hubble showed him evidence for the expansion of the universe. And most scientists believed in that for millennia. Basically, the universe was eternal, static, unchanging. They couldn't believe that after Hubble, so they had to append onto it, concatenate this new feature that it wasn't steady, it was quasi-steady. So the universe was making a certain amount of hydrogen every century in a given volume of space. And that amount of hydrogen that was produced was constant. But because it was producing more and more every century, as centuries pile up and the volume piles up, the universe could expand. And so that's how they developed.
But slowly.
Very slowly. And it doesn't match observational evidence. But that is an alternative.
By the way, did Einstein think the steady state universe is infinite or finite? Do you know?
I would assume that he thought it was infinite because there was really, if something had a no beginning in time, then it would be very unlikely we're in the center of it, or it's bounded, or it has, in that case, a finite edge to it.
I wonder what he thought about infinity, because that's such an uncomfortable.
He has this silly joke. I'm sure you're familiar with his silly joke, right?
What's that?
His silly joke was that there are only two things that are infinite: the universe and human stupidity. And I'm not sure about the universe. So,
well, me saying I'm not aware of the joke is a good example of the joke. It's very meta. Okay, so All right. So sorry, you were saying about quasi
All the alternatives.
all the alternatives in the quasi steady state.
And the most kind of promising, although I hate to say that, people say like, what's your favorite, alternative, right?
This is not investment advice.
Inflation is not transitory. It is quasi-permanent. So a very prominent...
Sorry to interrupt. We're talking about cosmic inflation. So calm down, cryptocurrency folks.
That's right. Although the first Nobel Prize, and one of the first Nobel Prizes in economics was awarded for inflation, not of the cosmological kind. So most people don't know that inflation has already won a Nobel Prize.
It's a good topic to work on if you want a Nobel Prize. Doesn't matter the field.
Exactly. It's time translation invariant. So when we look at the alternative that's called the bouncing or cyclic cosmologies, these have serious virtues. According to some. One of the virtues to me, just as a human, I'm just speaking, as a human, one of the founders of the new version of the cyclic cosmology called the bouncing cosmology is Paul Steinhardt. He's the Einstein Professor of Natural Sciences at Princeton University. You may have heard of it. And he was one of the originators of what was called new inflation. In other words, he was one of the founding fathers of inflation, who now not only has no belief or support for inflation, he actively claims that inflation is baroque, pernicious, dangerous, malevolent, not to science, not just to cosmology, but to society. So here's a man who created a theory that's captivated the world or universe of cosmologists, such as it is. It's not a huge universe, but there are more podcasters than cosmologists. Some do both, but this man created this theory with collaborators, and now he's like, I joke, I'm like, Paul, you're denying paternity, like you're like a deadbeat dad. Now you're saying like inflation is bogus, but he doesn't just attack. See, this is what's very important about approaching things as an experimentalist. You got a lot of theorists on, and that's wonderful. And I think that's a huge service. An experimentalist has to say no. He or she has to be confident to say, like, I don't care if I prove you right or I prove your enemy wrong or whatever. We have to be like exterminators. And nobody likes the exterminator until they need one, right? Or the garbage collectors, right? But it's vital that we be completely kind of unpersuaded by the beauty and the magnificence and the symmetry and the simplicity of some idea. Like inflation is a beautiful idea, but it also has consequences. And what Paul claims, I don't agree with him fully on this point, is that those consequences are dangerous because they lead to things like the multiverse, which is outside the purview of science. And in that sense, I can see support for what he does, but none of that detracts from my respect for a man. Imagine like, Elon comes up with this like really great idea, space, and then he's like, oh, actually, it's not going to work. And, but like, here's this better idea. And he's like, SpaceX is not going to work, but he's now created an alternative to it. It's extremely hard to do what Paul has done. Doesn't mean he's right. Doesn't mean I'm going to like have more and more attention paid to it because he's my friend or because I respect the idea or I respect the man and his colleague, Anna Aegis, who works really hard with him. But nevertheless, this has certain attractions to it. And what it does most foremost is that it removes the quantum gravity aspect from cosmology. So it takes away 50% of the motivation for a theory of quantum gravity. You talked a lot about quantum gravity. You talked to people, eminent people on the show. Always latent in those conversations is sort of the teleological expectation that there is a theory of everything. There is a theory of quantum gravity, but there's no law that says we have to have a theory of quantum gravity.
So that kind of implicit expectation has to do ultimately with the inflationary theory. So in cosmic inflation. So is that at the core? So okay, maybe you can speak to what is the negative impacts on society from believing in cosmic inflation.
So one of the more kind of robust predictions of inflation, according to its other two patriarchs, considered to be its patriarchs, Alan Guth at MIT and Andre Linde at Stanford, although he was in the USSR when he came up with these ideas, along with Paul Steinhardt, was that the universe has to eventually get into a quantum state. It has to exist in this Hilbert space, and the Hilbert space has certain features, and those features are quantum mechanical, endowed with quantum mechanical properties. And then it becomes very difficult to turn inflation off. So inflation can get started, but then it's like one of SpaceX rockets. It's hard to turn off a solid rocket booster, right? It continues the thrusting, and you need another mechanism to douse the flames of the inflationary expansion, which means that if inflation kicks off somewhere, it will kick off potentially everywhere at all times, including now, spawning an ever increasing set of universes. Some will die stillborn, some will continue and flourish, and this is known as the multiverse paradigm. It's a robust, seemingly robust consequence, not only of inflationary cosmology, but more and more we're seeing it in string theory as well. So that sometimes two branches coming to the same conclusion is taken as evidence for its reality.
So one of the negative consequences is it creates phenomena that we can't that are outside the reach of experimental science.
Yeah.
Or is it that the multiverse somehow has a philosophical negative effect on humanity? Like it makes us, maybe it makes life seem more meaningless. Is that where he's getting at a little bit, or is it not reaching that far?
Well, no, I think those are both kind of perceptive. The answer is a little of both, because in one sense, it's meant kind of to explain this fine-tuning problem that we find ourselves in a universe that's particularly fecund. It has features consistent with our existence, and how could we be otherwise? The sort of weak anthropic principle. On the other hand, a theory that predicts everything, literally everything, can be said to predict nothing. Like if I say, Lex, you've been working out, you look like, you have been, it's great. You look like you're, about somewhere under 10,000 kilograms. Be like, all right, yeah, you're right, but that's horribly imprecise. So what good is that? That's meaningless. I don't contribute any what's called surprise or reduction in entropy or reduction of your ignorance about the system, or exactly how much you weigh. So me telling you that tells you nothing. In this case, it's basically saying that we're living in a universe because the overwhelming odds of our existence dictate that we would exist. There has to be at least one place that we exist. But the problem is it's a manifestation of infinity. So humans, and I'm sure you know this from your work with AI and ML and everything else, that humans, as far as we know, really are the only entities capable of contemplating infinity, but we do so very imperfectly, right? So if I say to you, like, what's bigger, the number of, water molecules in this thing, or the number of real numbers? Or if I say, what's bigger, the number of real numbers or rational numbers? They're all different classifications of the amount of infinities that there could be. Infinity to the infinity power. We have kids someday, they'll tell you, I love you, infinity. You have to come back, I love you, infinity plus one,
yeah.
Right? So, but the human brain can't really contemplate infinity. Let me illustrate that. They say in the singularity, the universe had an infinite temperature, right? So let me ask you a question. Is there anything that you can contemplate in the Einstein's little quip aside, that's infinite? Like a physical property, density, pressure, temperature, energy, that's infinite. And if you can think of such thing, I'd like to know it. But if you can, how does it go to infinity minus one? The opposite direction I go with my kids. How does it go from to half of infinity? Because that's still infinity. How did it cool down? How did it get more and more tenuous and rarefied? So now it's only infinity over 2 in terms of Pascal.
Less infinite, more infinite. Yeah, I mean, it's that's one of the biggest troubling things to me about infinity is you can't truly hold it inside our minds. It's a mathematical construct that doesn't. It feels like intuition fails, but nevertheless we use it nonchalantly, and then use, like, physicists. They're incredible intuition machines, and then they'll play with this infinity as if they can play with it on the level of intuition as opposed to on the level of math. Maybe it's something cyclical. You can imagine infinity just going around the same, kind of like a Mobius strip situation. But then the question then arises: how do you make it more or less infinite? All of that intuition fails completely.
And I mean, how do you represent it in a computer, right? It's either some placeholder for infinity, or it's 1 divided by the smallest, possible, real number that you can represent in the memory.
Well, that's basically my undergraduate study in computer science, is how to represent a floating point in a computer. I think I took 17 courses on this topic. It was very useful.
So I came to the right place. But in terms of what a physicist will mean, and you're right. I mean, physicists will blithely, nonchalantly subtract infinity, renormalization, and do things to get finite answers. And it's miraculous. But at a certain point, you have to ask, well, what are the consequences for the real world? So one of them, you ask, well, what's the problem? Does it make us more meaningless? They purport, many of the people that support it, like Andre Linde. In fact, Andre Linde says, you have a bias, you, Lex, me, Brian, you have a bias that you believe in a universe, but shouldn't you believe in a multiverse? What evidence do you have that there's not so he turns it around. Whereas Paul Steinhardt will say, no, if anything can happen, then there's no predictive power within the theory, because you can always say, well, this value of the inflationary field did not produce sufficient gravitational wave energy for us to detect it with BICEP or Simon's observatory or whatever. But that doesn't mean that inflation didn't happen. And that's logically 100% correct. But it's like kind of chewing, Wonder Bread. I'm apologize if they're one of your sponsors, but reminds me of
Wonderbread/Lex.com.